All right, let's jump right in. We're going to tackle a real-world problem today, something that seems kind of complicated on the surface, but we're going to solve it with a surprisingly simple little map. So get ready, because we're going to learn to think like a painter, and yeah, a little bit like a mathematician too.
So picture this. You land a new gig. You're supposed to paint the hallways at a school. The paint's ready, the brushes are clean, you're looking at the floor plan. Seems easy enough, right? But there's always a catch. The school wants you to be as efficient as humanly possible.
And that is the heart of the puzzle. It's not just about slopping paint on walls. It's about finding the one perfect route that lets you paint everything you need to without taking a single wasted step. No backtracking, no wandering around. How in the world do you plan for that?
Now, like any good puzzle, there are rules. You only have to paint certain walls, the ones marked in red. You've got to cover all the outside walls. But here's the real kicker, the part that makes this tricky. For the interior hallways, you have to paint both sides. That means you'll have to travel down some hallways twice, and that's what makes this such a fun little problem to solve.
So when you're faced with a messy problem like this, what do you do? Well, the answer isn't to just stare at the complicated blueprint for hours. No, the secret is to make it simpler. We're going to create a whole new drawing that cuts through all the noise and just shows us the core of the problem.
And this amazing tool we're going to use is called a vertex edge graph. Now, I know that sounds super technical, right? Like something from a college math class. But trust me, it's just a fancy name for a map made of dots and lines. And it is absolutely brilliant for finding the hidden patterns in pretty much anything.
Okay, so before we can build our map, we gotta learn the language. The good news? It's incredibly easy. We only need to know two little words: vertices and edges.
First up, a vertex. The plural is vertices. And all this is a dot. Seriously. For our painting problem, we're going to put one of these dots at every single spot where hallways cross each other. Think of it as a crossroads, a point where you have to decide which way to go next.
And the second word, an edge. An edge is just a line that connects our dots. It connects our vertices. And for us, each edge is a wall that we have to paint. So if a dot is an intersection, a line is a paint job. See? I told you it was simple.
All right, theory time is over. We know the lingo. Now let's get our hands dirty. It's time to take that messy, confusing school floor plan and turn it into our own clean, simple vertex edge graph. Let's build this thing.
Here's how we do it. It's a simple three-step process. First, you look at the floor plan and you just find all the intersections. Second, you plop a dot, a vertex, on every single one of those spots. And finally, for every wall that needs paint, you just draw a line, an edge, connecting the two dots at either end of it. That's it.
Now get this, because this is the really cool part. Your new map doesn't have to be pretty. It doesn't have to be to scale. The lines don't even have to be straight. None of that matters. All we care about is the connections. Which intersection is connected to which other intersection? That's the only information we actually need.
Okay, but I can hear you thinking, wait a second, what about that tricky rule? The one about painting both sides of the inside walls. How do we possibly show that on our simple dot and line map?
Well, the solution is actually pretty clever. An exterior wall just needs one coat, one pass. So we represent it with one line, a single edge. But an interior wall, that needs two passes. So you guessed it, we represent it with two edges connecting the same two dots.
And the way we draw this is super simple. To show those two different trips down the same hall, we just draw a second line between the same two dots. It helps to make one of them curved just so it's really easy to see at a glance that, yep, there are two distinct paths there, two jobs to do.
So after all that work of translating the floor plan into our new map, where are we? Well, now that we have this simple model, the solution to our big, complicated puzzle is suddenly right there in front of us.
I mean, look what we've done. We've taken all that clutter from the blueprint, the room numbers, the doors, the exact measurements, and we've just boiled it all down to its absolute essence. All we have now is a clean, simple map that shows us what really matters, the intersections we can visit, and the paths we have to travel.
And here's the magic. With this graph, the hard problem of finding the most efficient path turns into a much simpler question. Can you trace over every single line on this drawing without lifting your pencil? That's what mathematicians call an Eulerian path. And just by looking at how many lines connect to each dot, we can instantly tell if it's possible, and even where we need to start and end. The graph doesn't just show us the problem, it gives us the answer. You know, this way of thinking goes so far beyond just painting hallways. Think about it. Planning the most efficient route for a delivery truck? That's just a map of dots and lines. Designing a computer network or even understanding how diseases spread? Dots and lines. So I'll leave you with this. What complicated problem in your world might suddenly look a whole lot simpler if you just imagined it as a collection of dots and lines?